Welcome to all. Myself, Dr. Santhosh Singh, working as a associate professor in Department of Physics, Institute of Aeronautical Engineering, Hyderabad. Today, I am going to discuss about energy bands in solids. It is the part of our semiconductors optoelectronic course. So, in my last video lecture, I have already given some primary information about energy bands in solids. So today I will extend this idea and I will discuss this thing in brief. So what happened? Why energy bands are arises in any solids spectrum? So here we considered one atoms which have only one electron, means it is a hydrogen atom case. You can consider hydrogen like atom. So in quantum mechanics this relations hold, or it is a general form of Schrodinger equation also. H psi is equal to E psi. So H is what? Total Hamiltonian, means total energy, or it is Hamiltonian operator, you can say also. So this on this operator, if this wave function if these operators operate on this wave function, this total energy operator operates on this wave function psi, then what they will give? The energy eigenvalue E, total energy. Why? Because this is total energy operator. So this is the very well-known equation in quantum mechanics, that is S psi is equal to E psi. And if we extended this idea and we deduce this equation in their terms, we can write H is what? Total energy, then H is equal to what? If H is total energy, then H can be written as a sum of potential energy and its kinetic energy. Okay, so potential energy is what? P square upon 2m. Kinetic energy, kinetic energy is what? P square upon 2m, and potential energy is what? You can consider V. So what I am talking about this considered system, this hydrogen like atom. Okay, so here this electron is revolving around this central nucleus, which having a positive charge E plus E, and this electron having negative charge E, quanta of charge, but in negative. This is positive charge. So this electron is revolving around this nucleus, then definitely it's have its kinetic energy, and also due to interaction among this positively charged nucleus and this electron, this system also have one potential energy. Okay, so this type of potential here can be written as a, means if two charge separated Q1, Q2, two charge separated apart a distance r, then what is the potential energy? V is equal to minus Q1, Q2 upon r 4 pi epsilon naught. Okay, so here Q1 is what? E. Q2 is also minus E, then it will goes like minus E square, but one minus is already present there. So it will be like minus E square upon R 1 upon 4 pi epsilon naught. Okay, so actually this potential energy term is Q1 Q2 upon R. Generally potential energy formula is Q1 Q2 upon R 1 upon 4 pi epsilon naught, not minus sign. Okay, minus sign you will consider for this electron. Okay, so what you will get? Minus E square upon R 1 upon 4 pi epsilon naught. Okay, so that is the case. This is the potential energy when one electron is revolving around one positive charge nucleus. Okay, so And what is the kinetic energy? It is P square upon 2m. So you can easily put this thing in considered our famous Schrodinger equation, that is del square psi plus 2m upon h square h cat square upon E minus V psi. Okay, means this is E is what? Total energy. V is what? Potential energy. So you can put all this potential energy term here. So what you will get, and after solve this Schrodinger equation in terms of their energies, you will get En is equal to minus me to the power 4 8 epsilon square h square upon 1 upon n square. Okay. So these are the energy eigenvalue. You can see this whole term is constant. Why? Because m is mass of electron, E is charge of electron, epsilon is also constant, h is Planck constant. So, and you also know the value of all these entities. Means you know the charge of electron, value of Planck constant, epsilon naught is what? Permittivity of electric field. So you also know the permittivity in free space of electric field. So you can put, and what you will get? You will get this equation. So energy of an atom where one single electron is revolving around one positively charged nucleus, then what type of energy you will get? You will get En is equal to minus 13.6 n square eV. Okay, where n is number integer 1, 2, 3. It should be either 1, 2, 3, not in a fractional form. So what you will get? You will, if you plot this energy, you will get the sharp labels. Okay. So that is the fundamental things when people start the thinking about the bands. Why? If first they solve the case of hydrogen atom. Here we already, in this case, this is the hydrogen atom case. So okay, what we will get? We will get the sharp energy levels, discrete sharp energy levels of isolated atoms are atoms having one electron. Okay, sharp discrete energy levels. This is your energy level. So this is the case of single or isolated atoms and then also having one electrons. Now these, if whatever the levels here we found here, simply I presented here in term of E1, E2, E3, E4, E5. Okay, simply for just sake of convenience, for qualitative presentation, just I given the name of these levels and also their energy value. This is not an exact energy value, for sake of understanding, okay, or for qualitative presentation only. This is not an exact thing. So in this axis, I have taken energy in electron volts and whatever the label we found for isolated atom, I characterized these labels with the name of E1, E2, E3, E4, E5. So here just remember these labels energy value. Means here E1 is what? Where this E1 level found? It is found at energy around minus 3 electron volts. So if I ask what is the energy value of E3 level? So here minus 1 electron volt. This is the case of isolated atoms. Now isolated atom or single atom. Now, if solid obviously comprises with number of atoms, not a single atom. So that's why now I am considering two atoms, A and B, not the isolated atom. And but the case here, the distance is these two high, so that these two atoms A and B are not interacting with each other. Means this is the case of non-interaction of atom. Means A is not interacting with B and B is also not interacting with A. Okay. There is no interaction at all between A and B. Why? Because this distance D, remember this distance D, is too far, and these two atoms are too apart from each other. That's why they are not interacting with each other. Now again we can solve the Schrodinger equation for these two atoms, and again we will get the sharp energy levels for both atom individually. This is for atom B. If I want to draw, then I will get the same thing for atom B and same thing for atom A. And if we plot these two atom energy states simultaneously, what we will get? We will get a single diagram. Each label exactly coincides with other one's label. Each labels of each atom exactly coincide with other atom's energy level. Means same E4 value at 1 electron volt. Here also 1 electron volt. E1 value minus 3 electron volt. Here also minus 3 electron volt. So if you draw these both atoms energy levels on a single plot, you will get either this graph or this graph. You can't distinguish. Okay. So again you will get what? A sharp levels only, not a band. This is the case of non-interacting atoms. Okay. What I consider non-interacting atoms. Two atoms, but they are not interacting with each other. Okay. Now, if D1, now this is the case D1, new distance, but it is less than D, whatever the previous case, D. So in this case, D1 is less than D, then these atoms start interacting with each other. They start interaction with each other. How? I already told each atoms have their wave function. So these wave function try to overlaps with each other at certain region or at certain extent. Okay. Why? Because this distance D1 is close enough so that they start interaction. Means their wave function are try to overlap with each other, or they are trying to mix with each other. Okay. That thing representing the wave function or wave associated with these atoms, or whatever the particle inside these atom like electron. Okay. So what you will get? Now these two atoms A and B in this case interacting with each other. Now again if we solve the Schrodinger equation for these two atoms, and again whatever we will get again this energy levels for these two atoms, and if we plot these energy levels, what we will get? We will get same energy value E1, E2, E3, E4, E5 for both these two levels, two atoms, but their value, see, in previous case, when atom is not interacting, E1 is around -3, E2 is around -2, E1 is around -3, E2 is around minus 2, E3 is around minus 1 in both cases. Now here see, for one case E1 is minus 2.9. Here one case they decrease the energy value, but in second case in atom B, for atom B, the E1 energy value little bit shifted at downside, minus 3.1 electron volt, but in this case it will be shifted little bit upside, minus 2.9. But in non-interacting case both should be around 3. But what you will get here? You will get here not exactly 3, but it will be nearby 3. One is positive side, one is little bit negative side. And this will happen for all energies value. See here. Okay. And if you will plot these two plots on a single graph, what you will get? You will get this thing. Two bands, two closely spaced sharp labels. I am not telling here bands. Here itself, here what is called energy level, sharp energy level. Here also you can say energy level, not bands, but two closely spaced energy levels. This is the case of only two atoms. Only two atoms. When they are interacting. See? Now your solids is comprises with n number of interacting atom. N number of interacting atoms. N number of interacting atoms. Solids. Okay. This is your real case in solid. So what you will get? You will get closely spaced n sharp labels. Closely spaced n sharp label for n interacting atoms. In this case, you will get for these, if you are considering two atoms, you are getting two sharp energy level. If you will consider n interacting atom, you will get what? N in sharp level of energy. Sharp levels of energy for each particular energy. Okay. This is even. So here n very closely spaced n numbers of energy level. Okay. So what you will get? You will get a picture like. You will get a picture like. You can't distinguish each energy level with another. Okay. For particular energy even. So it will be appear like a band. Okay. So this is your E1. Again for E2 case, one another band will appear. For E3, again one another band. Same for E4. Same for E5. So why the band is arises? Band is arises due to interactions of atoms. Why? Because in solid, the interatomic distance is too close, so that all the atom inside the solid interacting with each other frequently. That's why the sharp energy levels turned into a band. Okay. Turned into a band formation. See here. Okay. So the same thing is written here. In an isolated isolated atom case, atom have discrete sharp energy level. Discrete sharp energy level. See here, isolated atom. Okay. In the case of two identical atom, when the interatomic distance between the atoms too far so that these considered atom could not interact, then the same energy spectrum occurs like a single isolated atom. Okay. Same. When non-interacting case here also. Here the case of two atom, but they are not non-interacting. So same energy levels occur like isolated atoms. Okay. Now, what is the third case? When interatomic distance decreased in a such extent that atoms start interaction with each other, then energy level of considered atoms slightly perturb. Slightly perturb. Here. Now, previous it is 1, but in this case 1.1. Previous this is 1, but this is case minus 0.9 electron volt. Slightly perturbed. Okay. Slightly perturbed. If more atoms are brought together, consider an atom in case of solid, then each energy level is split into closely spaced n labels. These labels are so close together that they form a continuous band. They form a continuous band. Means if there are large number of atoms, that is the actual case or practical case. So, and they are closely spaced. Why? Because solid is a dense material. So they are closely spaced. Means at that time they start interacting with neighboring atom or all the atoms. Then whatever their energy level, they are slightly perturbed with the influence of other atoms. And that time if you plot the energy levels, you will get what? You will get the band, not a sharp energy levels. Okay. So here the same thing, bands are given. These are bands, these are bands, these are bands. Okay. Means here a large number of energy level inside this band. This thing is known as a width of band. Width of band. Okay. So width of band depends on the degree of overlap of wave function. Degree of overlap of wave function. Or interaction means how much the atom are interacting with each other. Okay. How much the atom are interacting with each other. So in terms of quantum mechanics, if the wave function are too much overlap with each other, this broadness will become high. Okay. If they are slightly interact, then these bands will become narrow. Okay. Not broader. Means non-interacting case, you will get like energy levels. Simple. Okay. So what is the actual situation? In actual situation, this is the actual graph. Actually, for when in this, suppose this is your x-axis, this is your energy value on y-axis, energy. In electron volt on y-axis, this is your y-axis, and on x-axis what is interatomic distance, interatomic spacing. Means suppose this is your atom, this is your atom. So this is the first case. When interatomic spacing is too high, means if this distance is too high, then these two atoms are non-interacting case. Then you will get what? Sharp energy levels. Okay. sharp energy levels. Also, you can say, for considering only these two levels, you can say this is the case of insulator. This is the case of insulator. Okay. But when you reduce this distance, suppose this is D, here D. So this distance is greater than D. Now you are reducing this distance D. Now, then here's some region here you are, okay. This is your D. Now you are reducing D1 here. This is your D1. So in between D1 to D you are. Then what happened? These levels start perturbating, start splitting. Actually, this is not a one level splitting. These are two levels actually. Okay. These are two levels. The same levels. Why? Because here no interaction. So all level for these two atoms, all levels coexist on one and another. But here, when the atoms are start interacting, these levels starts splitting. Okay. So here in the case, at some extent, the band gap exists. Now the band is forming. Band here. See band. Band. At this level, this is your band width. At this level, this is your bandwidth. This is your bandwidth at this level. So both these bands overlap with each other here. But here bands are there. But there are some gap also. So this is the region of semiconductor, you can say. Means at some particular case it will behave like a conductor. Why? Because these bands are overlapped. But at some condition it behaves like a insulator. Why? Because band gap also exists. So you can say this is the region where you can define a semiconductor. Here perfectly overlap means this is the case of metal. But when you are at this distance, suppose here, so here what is the band? This is the band, this is the band, again band gap. Metal case is from here to here only, perfect overlap. Okay, but here again the same semiconducting region you can say start. Why? Because again some band gap value exists. Okay, so this is the exact case. Now I want to give some exact situation. I want to give an introduction of some exact situation, how the atoms situated inside the solid. So actually atom, one scientist named Chronic Penny, he produced his model. He come forward with his model. What type of model? He tried to modeling the atom's position inside the crystal. Okay. So what he suggests? Atom is situated inside the crystal in a potential well. Potential well. Okay. This is your atom, and a potential well is formed around these considered atom. Okay. Actually, suppose this is 1D array of atoms. So actually the potential is very like that. Why? Because suppose any charged particle Q, the potential variation in potential like that. This is distance R. So at R distance like that, at when R becomes 0, it will become asymptotic. Means like infinity. Okay. So if you consider one dimensional array, the potential variation due to charge presence inside the crystal, the potential variation is like that. But you can't solve Schrodinger equation for potential variation like that. Why? Because here you can't say what is this is infinite term, na? So you can these are infinite term, asymptotic. So you cannot solve the Schrodinger equation for this situation. Okay. So what happened? Kronig and Penny come forward. Kronig and Penny. That is famous as a Kronig-Penny model. Kronig-Penny model. Come forward with his idea, and he suggested that this is not a infinite well. This is a finite well, and atoms are arranged in a finite well potential. Okay. In some text, it is like that. Periodic potential means come here, 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 here. So this is one period. Okay. Why? Because these atoms are spaced at an equidistance. Okay. So these periodic potential, that's why this potential also have some periodicity. Okay. So suppose this is your case where x is equal to 0. So, and this is A, this is your B. Okay. So potential is, this potential value is, suppose this is here V naught and here 0. Potential value is 0. So from this point to this point, when x is in between B to A, the potential value is what? V naught. And elsewhere the potential value is what? V0. 0. So this is the case Kronig-Penny suggested. The atom is situated in a periodic potential well. Okay. So he also solved the Schrodinger equation for this condition. That is a long mathematical formalism. I will not go in all details. So what they will get? He will get a wave-like solution. Okay. So this is, he come with idea. this is the bands. These are the allowed energy states characterized as a bands. Here no allowed energy state, that is known as a forbidden gap. Okay, so one thing, exact inside the crystal situation inside the crystal structure, one scientist named Cronin and Penny also tried to solve the Schrodinger equation, and he also found the band-like things. Means there are some allowed energy level, closely spaced allowed energy level, and there are some forbidden energy gap, means non-existence of energy levels. Okay, you can also see in terms of interacting potential well. Same thing. Suppose this is the case where one particle is inside the potential well. Okay, so one particle and one potential well, then there is only one solution. If you will solve this case, if you will solve the Schrodinger equation for this case, you will get only one solution. Means there is one wave function. If suppose there is two potential well but non-interacting with each other, so there are still one solution. But if they are, and this is the separation between these potential well D. If you decrease this separation D, what you will get? What happen? These potential well start interacting. Okay, so not only single solution but two solution. Okay, similarly if three, same case. So again they start interacting. So in each case there are three solutions for each particle. Okay, so similarly, if again you will plot this thing, when the single non-interacting potential well, there is only one solution. If there is only one number of potential well, if two number of potential well, then two solution. If three number of potential well, then there is three solution. If there is four number of potential well, four solution. So again, if n number of potential well, then n solution. This is exactly solvable by quantum mechanics. Okay, so these things are known as a bands. Okay, so that is the basic idea why the energy bands arises in solid. So thank you for your patience.
Like, share and subscribe. Hit the bell icon for more updates.